Alright, this is the second video about my freshman year project at LTU. This is going to be talking about VoxWorld. It's a voxel game engine written in C++ with SDL2 and Glue for my helper libraries. SDL2 manages all the window creation, and Glue wrangles all of the function names for OpenGL. The only requirements to running it are SDL2, SDL2 TTF for the text generation, and Glue. As long as you have those three libraries, you should just be able to run make on any Linux computer. And there is a branch for Windows if you're curious, but it's behind a little bit. You're gonna want MingGWW64. So if you want to try to follow along, go for it. This is going to be a video displaying the different types of world generation that I've implemented. The first one being this. This is two-dimensional Perlin noise generation. So the way that works, I'm using 4 different octaves of Perlin noise and just adding them together to create a height map for the world, and then it just fills in the mountains according to that height map. If you are curious about what Perlin noise looks like, I will show you. So, let's find a good picture here. This is a good picture. So this is roughly what a single octave of Perlin noise will look like. Of course, it's entirely procedural, meaning based on what you seed it with, you'll get a fully random picture. But essentially, the dark spots are valleys and the white spots are mountains, and you slowly transition over a whole bunch of these little bumps over and over again in a very uniform looking, kind of smooth, bumpy texture. Think of like an orange peel or something. And then what an octave of Perlin noise is essentially specifies how big those lumps are. So an octave of 1 says that maybe from, on average, a single peak to terrain is going to be a certain distance, and then twice the size, or twice the octave size, is going to be twice as big there. So all you do is generate a whole bunch of different Perlin noise sets at different octaves and add them together, and that will produce an image that looks something like this, which is essentially what's happening in the program. The next type is going to be three-dimensional Perlin noise, and this is a little interesting. So the way it's changed is through this chunk generator pointer here, right here. Oh, I'm in the header file. I don't want to be there. Alright, so we're going to change chunk generator Perlin 2D to 3D. Hopefully I've got the name right. I don't. I will quickly look it up in GitHub here. Perlin. Simply Perlin, not 3D. Now, this three-dimensional Perlin noise is going to be a lot slower to generate in, because for the height map, a single chunk is 64 by 64 by 64 blocks. The height map only has to do 64 by 64 little pixels, or little generation calls, where the Perlin noise three-dimensional here has to do 64 cubed little mass generations. And this is an example of a very smooth world. The things that you get are overhangs like this, where with a height map you can't get any overhangs. So you simply have a single a height of every point, and you need 2 heights to get anything like this. So this is an example of a very flat, smooth terrain generated with three-dimensional Perlin noise. We can also go in and get rid of this, and this will look very interesting. Generates in here. There we go. So this now is three-dimensional Perlin noise, but it doesn't get smoothed out the higher you are. So I showed you a picture of what two-dimensional Perlin noise looks like. Well, this is what three-dimensional Perlin noise looks like, where instead of being a flat set of bumps like an orange peeler, so this is the three-dimensional set of little bumps that slowly transition from voids to dense spaces. And again, this uses the same principle where you have a whole bunch of different octaves all added together. Although currently this is only running one octave, or maybe two. If you want to add more, it's fairly simple. So you can go into here, and we will add another octave, and it's quite easy to do. All you have to do is literally add another octave. You see, I was scaling the y, or dividing the y-axis by 2. Should probably set this to something like that, and we should weight this one slightly lower, or a lot lower, like 0.2 and 0.8. So it's a little bit of experimentation. Let's see what this looks like. It's going to now take twice as long to generate in, unfortunately, but that is just the nature of Perlin noise in 3 dimensions. Games like Minecraft, the way they overcome that problem is, well, what they do is, instead of generating Perlin noise three-dimensional Perlin noise for every single block, they do it like every 4 blocks and then interpolate between them. But I haven't been super interested in that yet. So what this did, you can see I have the same kind of thick Perlin noise smooth walls, but then there's this other little set of Perlin noise that gets added and subtracted onto all these little things to kind of grow little lumps onto the edges of the cave here. See if we can get rid of some of this dirt and grass and see what that does. Possibly not. I don't know. It'll be a little slow to do. See, the next chunk generation that I can look at would be, it's a good one. I know what I can do. So I have one more thing to show, and that is the diamond square train that I've made. So the work in progress branch. I'm gonna have to fix a quick bug here before I can run this. On line 191. So, oh look, it looks like it's already been fixed. I take that back. Must have not later or earlier. I mean. So what this is gonna show is every single chunk is basically seated, or its height is seated at each of the 4 corners, and then it creates a flat, or a flat if possible, surface between those 4 points. And that creates something kind of like this. So you can actually see the chunks here. So right here is the corner of a chunk, right here is a corner of a chunk, and right down here is a corner of the chunk, and it kind of generates the 4 corners of that chunk with Perlin noise, two-dimensional Perlin noise, and then it smooths out the height of that entire thing across the chunk. Normally, when you use diamond square, you'd also add a little bit of randomness, and you do the entire thing like that, and it'll look like an actual mountain. However, that was not the point of me doing the diamond square like that. Instead, what you can see in the background here is my attempt at a level of detail mesh. And basically, the way this works is the way the diamond square algorithm will calculate a mesh will look exactly like a single 4 triangle per chunk mesh that we can create out of the Perlin noise generation of that chunk. So you can see only the middle third or so of this world is actually being generated and rendered with triangles, or with actual blocks and small triangles, and the rest of the world out in the distance is all rendered as very low detail data. So that I think that's about all I have to show you. So yeah, thanks.